Remember that you're looking at the sum of all of these slices from there all the way up to there. If you make them infinitely thin, it's just the height of the function is the radius, right? Height of the function is the radius. The thickness is dx, right? If you push them really skinny. The area of that thing is obviously pi r squared. So pi times f of x squared. If the cross sections are all circles, like you could extend this where the cross sections are other shapes, which is what we'll do in the last section in this unit. If there's squares or if there's something else, right now there's circles, and so the area is the height of that function squared times pi. So if you go back to this is in general what the volume formula is. Specifically to volumes of rotation, yes. This is if you're rotating around the x-axis. If you're rotating around the x-axis, it's just whatever the function is. If you have some function like this that looks like whatever here, called f of x, and you want to know the volume of rotation from A to B like this, as in if you rotate that whole area around, it's just integral of f of x squared times pi. And if you want to put the pi first, you can. You could actually take the pi out, which is probably the best thing to do normally, because that the area of one of the cross sections is just this, right? This is that. This formula is specific to the fact that if you're looking at if you're rotating this, right? Somebody could say we could make a shape where there are squares that are the height of this curve, right? In which case it wouldn't be circular cross section or whatever, right? Any kind of shape here. If somebody said, well, let's make a shape where all the cross sections are squares, it's still the same formula. It's just that the area of each cross section would be different. Okay? The basic general volume formula is this. The integral from whatever your two limits are of the area of the cross sections. This is area of cross sections. Well, you wouldn't, I just put A of x, and in this case, I'm just using A of x to say the area of the cross sections.
Well, what about the other one that's the square root of x? How it changes make a difference?
Yeah, whatever the function is here, like this. For this one, if you want the volume from, this looks like to 2 here, right? The volume of that is going to be integral from 0 to 2 of square root of x squared times pi. Right? Because square root of x is the radius. Let's try that again. Square root of x is the radius. This thing right here is the radius. The height of that function is the radius. The value of the function, and that's important to see, the value of the function is the radius of the circle. Okay? F of x, or in other words, in this case, it's square root of x, right? That's squared times pi, because it's pi r squared area of a circle times d of x. This is what the volume of that shape would be. Okay, it's not as impossibly hard as, yeah, absolutely, right? Let's look at some specific ones here. I'm calling those things disks, right? These shapes that we're using, these thin cylinders, these flat cylinders, we're calling them disks in here. This is essentially the thing that I just gave you, except that we're only going from 1 to 4. You could draw the thing for yourself. There's the curve. And you want to go now from 1 to 4. There's 1 and 4, if you extend this out a bit. So you have a shape where you're rotating this area around. So what is that going to look like if we create that shape? It's not going to look like a bullet. It's going to look like a bullet with a flat front on it, I guess. Let's let's maybe think of more positive things than bullets for everything. What does this look like? Looks like a bullet. Maybe I should refer a few of you to the counselor.
Like a popcorn bowl.
Yeah, see, now you're thinking better. A popcorn bowl. There's going to be, I think we should have a creative part of the calculus course is describing what you think the shape will be, right? I think it's a lampshade. I don't know. I think it's a whatever. If you had to draw it, I guess I should draw it in the same orientation here. So you have a circle right here. And something like that, right? It would be more flat. I have it curved too much, but we'll go here and we'll say we want to go now from, what was this now? It was from 1. We'll pause while I fiddle around. I hope you're okay.
Yes, it is. Which one?
So you're doing integral from 1 to 4 pi times f of x squared, right? Or whatever it is, dx. Or in other words, the function that it is root x squared, right? The area of one of the cross sections, the area of this thing, right, is that blue part there, pi times that squared. Although it's easier if you work it out by putting the pi outside here, because then you're using your calculator, you can turn it into a fraction without worrying about the pi. Root x squared is just x. So you could use your calculator. You could do this one analytically. Doesn't matter, right? Whichever way you want. Calculator or using algebra. 1/2 x squared evaluated from 4 to 1 times pi, right? Leave the pi out of the whole thing. This is going to give you 16 over 2 minus 1 over 2. 15 over 2, right? Times pi. 15 pi over 2. That's doing it analytically. Of course, you could go on the calculator and just put in that integral and find that. In this unit, it doesn't matter which way you do it. You could do it analytically. You could do it on the calculator. If you were to put it on the calculator, you go to your numerical integration here. Integral of, you put the original function. Don't start doing analytical stuff yourself here if you're using the calculator. It's one or the other. You put the variable in, x, and you put 1 and you put 4. That should give me the same thing. Notice I'm leaving the pi out because I want to be able to turn this into a fraction. Oh, I didn't square it. You're right. I could just put x. You're right. Right, thank you. And so, of course, you want to turn that into a fraction, turn that into a fraction. And then don't forget the pi on there, right? 15 pi over 2. That's the volume of that thing. That's summing up all the slices from one end to the other. Now, the difference comes later on here if we start doing area between two curves. So not this question, but the one after that. I'm going to stop and restart this thing before we do that. This one? Same thing, right? As we just did. This one is this. And it's just between that. It says from, you're still rotating around that axis, but it's up to this, up to 2, right? You're just defining the region a little bit differently, right? You're doing this region right here around. So what is that going to look like? Thank you. So this is, it looks like that, except it was starting at 0, wasn't I? This one is 0. So it's starting from there. You can fiddle around with the limits if you want to make it look, if you want to equalize the axes or something like that, if you want to know the actual shape of the thing. But it looks like that, right? There's there's a shape of it, sort of like that, whatever shape you guys are talking about. You find the volume of exactly the same way, though, right? Integral from 0 to 2 of x squared dx. X squared squared dx. 10 minutes. Pause. Let me say that again for the viewers at home. Try this one. This one is the y-axis. If you're rotating it, this one you can't, like, now you don't have a choice if the circles are going one way or the other, right? When you're rotating it, you don't have a choice. If you want this area, you could do it between, you could do rectangles this way, or you could do rectangles this way, except if we're actually rotating them, you have to do it in the direction that they're being rotated. And I just